Hi, I'm Jack Baker. This section, we're going to talk about measuring properties of stochastic processes and dig a little bit deeper into some uncertainties associated with estimating power spectral densities from real-world signals. So, through the class in general, we've been mostly concerned with kind of mathematical theory. We assume we've been focused on the cases where we have a description of a stochastic process and we want to get these characteristics of the process. But let's talk a little bit more in depth about analyzing measurements of data and using them to calibrate models for stochastic processes. As with kind of much of the rest of the class, we're going to be largely concerned with the power spectral density. So I want to dig into that a little bit and kind of what the properties of our estimators are from data. And the issue we're dealing with here is that, conceptually we've looked at this cartoon of kind of having multiple realizations of a process, in principle, maybe infinite realizations of a process over infinite time. But most of the time in the real world, we've got one sample or a few samples of the process. And further, that sample of the process is not going to be infinite in length. It's going to be finite in length. So we could think about having, say, the data in this red box. One realization for a finite amount of time. If it's only one realization, we need the process to be ergodic, of course. But even if it's an ergodic process, we're still going to have estimation problems from kind of finite data. And so let's talk about that a little bit more. So kind of in our first mathematical theory of the stochastic process, we said, we've got this process x of t. We are going to estimate a autocorrelation function for that process. And then we can take a Fourier transform of that autocorrelation to get at the power spectral density. Right? And it turned out that didn't work great. We had some estimation errors, and that it was kind of preferable actually to instead estimate the Fourier transform of x of t directly, and that can be used to get the power spectral density. And that's got better statistical properties. Although all I could really do is kind of show you some example data to indicate that that was the case. Let's look a little bit more in detail here today about kind of these estimating power spectral densities from autocorrelations, and particularly from finite length signals, and see what the implications are. And so if we're trying to estimate that autocorrelation, going back to the kind of the initial strategy, say, this autocorrelation is of interest, we can estimate it from the expected value of x of t times x of t at a lag t plus tau. So when it's a finite length signal, so the first consideration is that we can't estimate this or let's say when that time like tau, either positive or negative, is bigger than the length of the signal. Right? So big T being the duration of the signal today. So when we try to do this power spectral density calculation from the autocorrelation, we'd like to integrate it from minus infinity to infinity. We can't do that because we don't have the power spectral density from that top equation over all t. All right, so we end up with this situation where kind of theoretically what we would like to be looking at in that equation there on the left is a plot versus tau, where we've got an autocorrelation and then we're going to multiply that autocorrelation by e to the minus I omega tau, or equivalently, we can just multiply by cosine omega tau. We should label these plots, huh? Right, so that's cosine omega tau, some omega that we're interested in, and the red plot is the autocorrelation. But then what we're saying is that we've only got these things defined out to some interval from minus t to positive t. And we don't have these functions out beyond that. So our integral, we're going to have to make an approximation in this bottom equation, and we're only going to integrate from minus t to positive t. And that's kind of the best we can do. So this approximation here, we're interested in kind of what impact does that have. Okay. So an easy way to, or a way to get a little bit of intuition about this is let's just pick a specific process. So let's pick this process we've been looking at at various points in time in the class. We got a cosine omega naught t plus theta, where theta is this uniform phase change. It's uniform between 0 and 2 pi. So we've looked at this process before. Because of that phase shift, the process is stationary, and it's a narrow band process with frequency omega naught. Right? So we've done the calculations before on functions that look like this, and we know that the autocorrelation function, we've got this constant out front, a squared over 2, and then it's a periodic autocorrelation with this cosine omega naught tau. And then we know that the power spectral density has Dirac deltas at positive omega naught and minus omega naught, and they're scaled by the constant as well. Okay, so that's the correct answer. So we know this in principle for this particular case. And the question is, what do we estimate if we've got a finite length signal? So now let's assume we've only got from time t equals 0 to t equals big T. And so our power spectral density, if we estimate it from the autocorrelation, we'll say we're going to integrate from minus t to t of this autocorrelation. And then we'll switch to the form with the cosine omega t in there. So that's kind of like the picture I drew on the previous slide, where we substitute. So we're just substituting in the autocorrelation into this formula to try to estimate the power spectral density. So we've got this cosine omega naught tau times cosine omega tau term. And so with this double cosine, we can do our trigonometric identities. The integral of a cosine is sine, so we've got sine terms left over. And we've got these two terms, one of them centered at positive omega naught, and then one of them centered at minus omega naught. And then there's some kind of constants out front. But we've got the sine omega naught, omega minus omega naught divided by omega minus omega naught in here. And then the length of the signal t is kind of scaling how fast this thing is oscillating here. So let's look at what these results would look like in plots. So for the real process, if we had an infinite length signal, or we just do this mathematically, we know that the answer looks like the following. So the autocorrelation function is just periodic. It'll just continue on for off to infinity. So this is phi xx of tau versus tau. And the power spectral density for the real process, we know at frequency omega naught and minus omega naught. We'll have those Dirac deltas. Okay, so that's what we know to be the case. Our measurements are going to give us a slightly different result. So for the autocorrelation, this will be, let's assume we can estimate it perfectly as long as t is less than big T, or tau is less than big T. So same periodic function, just truncated from minus t to t. And because of that, the integral in the previous slide for the power spectral density gets us the sine omega t over omega. So what does that look like if we plotted that thing out? We get these power spectral density terms that are, again, centered at omega naught. This is versus them. So power spectral density for x as a function of omega. This top figure should be a function of omega also. Okay, so at omega naught, and at minus omega naught, we have those terms. And we have this sine omega divided by omega type of thing going. So it's going to be an oscillatory thing that's going to die down. So it looks something like this. So we get kind of not an infinitesimal spike in our power spectral density. We've got a little bit of loss of resolution in exactly what frequency the power's at. And we also get negative values out of the power spectral density, which shouldn't be possible, except for basically the substitution of an improper autocorrelation function has led us to see that result. Okay, so we've got kind of a general picture of what's going on in that power spectral density, but we've got this estimation error going on. And you can see that play out a little bit in the sea level data that we had looked at previously in the class. So here's power spectral densities estimated from autocorrelations and autocovariances. So here we're taking the Fourier transform of, say, the autocovariance and plotting that up. And we can see kind of our 1 per day and 2 per day frequencies from the tidal variation showing up. But we see this kind of negative power spectral densities coming out and see this kind of loss of frequency resolution a little bit. So that plays out kind of directly if we do this estimation this way. Okay, so that's kind of one indication of some estimation error. Let's look at another strategy for estimating these power spectral densities that'll also give us some insight into estimation error. And so this strategy, we're going to call it the frequency analyzer. And here the idea is we've got the signal x of t, and rather than trying to estimate it, properties from it directly, we're going to pass it through a filter. So we're going to start off with a realization of x of t. We're going to input it into a filter, and we're going to get a y of t out the back, and we're going to study y of t. Okay. And the filter, right, so one type of filter we've thought about is like a structure. That's our main kind of focus in this class. But we talked about mathematically a filter and a structure are kind of similar to each other in that they're doing some sort of operation on the input and giving us an output. And we can talk about filters via the frequency response function associated with them. So let's think about a filter, a little bit idealized, but this will help us understand the concept. So we've got a filter with a frequency response function, h of omega, as follows. So it's going to have a central frequency of omega naught. And the frequency response function is going to look like the following. We're going to have rectangles here for the frequency response function. Okay, and these frequency response functions, let's say they have a height h0. And let's say they have a bandwidth, the width of these rectangles here, we'll call it b for the bandwidth. And so how wide of a range of frequencies are going to get through this filter. All right? And then what we're going to do is we're going to compute the energy of the output. So we're going to look at the expected value of y of t squared, where y is this output. All right, so we know that the expected value of y of t squared is the area under the power spectral density. Of y. And because y is the output from this filtering process, we can also find the power spectral density of y as this frequency response function, this modulus squares, times the power spectral density of x, which is really the thing we're interested in. And because that frequency response function has such a special shape to it, we can say, well, the the area under this y power spectral density. Right? It's going to be the power spectral density of x evaluated at omega 0. Right? That's the frequency at which the middle of this kind of bandpass filter is letting things through. It's going to, the amplitude out the back of the y's is going to be h0 squared. So we take that frequency response function squared. And then the area under this function, we're going to have to think about the kind of the width of these rectangles too. So those rectangles have width b, and there's 2 of them, so we'll multiply by 2b as well. So that's just kind of a quick evaluation of the integral under the assumption that b is narrow enough that the power spectral density for x is not changing over that bandwidth. Okay. So there's a formula for this energy of the output in terms of the power spectral density of x. And then this thing on the left-hand side, we can estimate this from our sample of the data. Right, so an estimate of the mean squared would be take 1 over n times the sum over all the points, I equals 1 to n, of y at time ti squared. Right. So on the left-hand side, we can estimate that from our sample with the y of ti's. On the right-hand side, we know h0 and b, the properties of this filter that we specified. So the only thing we don't know is sxx. So we're going to solve for this, or solve for sxx of omega, just by rearranging this. Okay. So rearranging here on the next slide, here over on the left side is the thing we're trying to solve for in terms of these other properties. Okay. And then the idea for estimating the full power spectral density of x is we would just repeat this process with different filters. Okay. So we would have, it's kind of a cartoon. I'll leave off the left side here for a second. The frequency response function. So first we would say pick a filter with central frequency here. So that might be our first one. And then we'll repeat the whole process with a different filter that's got a frequency response function like this. Then we'll repeat the whole process again with the third frequency response function, and so on. Right? And each of these would have a corresponding negative value too, but I'll just make the picture a little simpler here and leave those off. Okay? And in reality, we could make these, push these frequency response functions to be kind of more adjacent to each other, but I'll leave them a little bit separated here just for ease of viewing what's going on. Okay, so that would be this frequency analyzer. Take a bunch of filters, study the energy of the outputs as a way to estimate the power at each one of these frequencies in the input x. Okay, so now let's think about the uncertainty in this process. Okay, so if that's my estimator up top here, and I'm going to estimate this from my data, so the numerator is actually going to be 1 over n sum I equals 1 to n y at time ti squared over 2h0b. So everything is a constant except for those y's. Those are the things that are giving me some uncertainty here. Right, so I've got y as a function of t here, and y is going to be a narrowband signal because it's the output from this narrowband bandpass filter. So it'll be some sort of a harmonic looking function. And we're going to have a sample up to length t. And if we take the sum of those terms squared, then we're going to have some sort of uncertainty depending on how long that signal is. And that's what we're interested in here. So in order to figure this out, let's define a new variable z, which is 1 over t times the integral from 0 to t of y of t squared dt. So this is just a continuous version of the discrete calculation I put up above. And it's an integral version instead of a summation version. And that's just a little easier to deal with mathematically because we can use kind of the same tools we've used previously for the continuous cases. The discreteness, would add another layer in there, but you'll get the concept here from looking at this. All right. So this thing here on the right-hand side, this is our estimator in the continuous case of y of, the expected value of y of t squared. Right. And then we're going to be interested in what is the variance of this estimator z. Right. So sigma squared z is going to be the expected value of z squared minus the mean of z squared. And that mean may or may not be 0. Okay, so to understand kind of this uncertainty in z, let's expand this thing out a bit. All right, so z is equal to this term in curly brackets. So z squared is going to be the square of that. We'll square it out. We'll just multiply one term in curly brackets by another one. In order to do this, we're going to have two dummy variables for integration, so we'll call them t1 and t2. If we take the expected value of that z squared, then we can move around expectations and integrals. So we'll bring the integrals outside of the expectation, and we're left with this expectation of y squared at time t1, y squared at time t2. All right, and so that thing is a little bit of a bear to deal with. It looks almost like an autocorrelation, except we've got squared values in there, so that's an extra complication. It turns out that you can do some manipulations. If the process is Gaussian, we can make a simplification down to an expectation in terms of just y at t1 and y at t2. That thing squared, so that looks like an autocorrelation, and then an expected value of y squared squared. Okay. So let's see. So let's look at this autocorrelation term a little bit more. All right. So let's assume y to be stationary, and so then in that case, this y at t1, y at t2, we can think about that as being the autocorrelation at time with just an argument of t1 minus t2 in it. That autocorrelation squared, and then this expected value of y squared as well. Okay. So we'll plug that back into the variance calculation. So the variance of z is going to be this expected value of z squared, which has got this autocorrelation term squared, and then the means of z kind of will cancel out of this thing. So that simplifies things for us a bit. Then, so we've got an autocorrelation squared over these, integrated over these terms t1 and t2. So you got to do a couple more manipulations. I'm going to skip the intermediate derivations. So one thing is we've got to change the variable of integration. We'll switch to tau, but then we have to change our limits of integration if we integrate with regard to tau. Then we've got a narrowband process, since y is the output of this narrowband filter. And so we know the autocorrelation for a narrowband process. We know its general functional form with that kind of omega naught being the central frequency. And then we kind of make an approximation in the integral to move things along and put it in a simpler form. And what we'll get out the back is that the variance of z is going to be equal to kind of 2 pi over b, 1 over t, and then the autocorrelation for y at a tau of 0. Right? So this thing here is the expected value of y of t squared, right, at any instant in time t. It's a stationary process, so it doesn't matter what t. And that's equal to the expected value of z squared, which is kind of the variance of z plus the mean value of z squared. Okay, so we've got kind of variance of z, mean of z, so on. We can rearrange a little bit, and what's kind of relevance to us here is that we can get the standard deviation of z relative to its mean being a function, the square root of 2 pi over b, 1 over t. And ultimately, we're trying to find this power spectral density for x at frequency omega, and it's this z that's kind of the estimator here. And so this is telling us kind of when is that z going to be uncertain relative to the mean value of z that we're trying to estimate. Okay? So to get a small standard deviation of that estimator of z relative to the mean, we need that term in parentheses, or the term in the square root to be small, which means we need the reciprocal of that to be big or much bigger than 1, which is what I've got written down here at the bottom. And there's 2 ways we can get that thing to be much bigger than 1. All right, so the first is to let b be large. So a big B will give us kind of less uncertainty. So what does that mean in terms of this whole operation? That means we need a big bandwidth on the filter. So if I back up, remember to slide 10, so B was this bandwidth. Right, so it's saying we should make that bandwidth bigger and basically let more frequencies through in this filtering step in order to get less uncertainty in C and less uncertainty in this power spectral density. Right? So what's going on here? It's saying if I let more frequencies through, I've got kind of more data to average out here and to estimate the energy. So I'll have less uncertainty, but that comes at a trade-off. Right? If I let a lot of frequencies through, then I don't really know exactly which frequency is associated with this power spectral density estimate that I've just come up with. So I'm going to lose resolution in my frequencies. So the trade-off here is that, while this is helpful for uncertainty, we would actually like a small b to get high resolution in the power spectral density in terms of the frequency domain. All right, so there's a trade-off. The good news is there's one more term in here that we might be able to use instead, a t. So a big T would also help us. What's that mean? That means a long window of time of observation. So if I can get a longer signal to use with this whole thing, then that will help me get lower uncertainty. And it would also let me have a smaller bandwidth so that this overall term still stays large. Okay? So we got this trade-off between how much data we've got and how much frequency resolution we're going to be able to obtain for a given level of uncertainty in our estimate. Okay? And so that's, it's useful if we think about gathering data. It also gives us a useful constraint if we think about some other analysis. So as an aside, we might think about, and maybe some of you in your projects are going to think about, say like an earthquake ground motion. And strictly speaking, those ground motions without some sort of manipulations are not going to look very stationary. So if I think about time and x of t being, say, the acceleration or something like that, if our ground motion looks something like this, we might say, well, okay, this process is not necessarily stationary. We see things like the frequency content being a little bit different in different portions of time. So I might say, let me divide, say, like the ramp up phase, and then some sort of a kind of stationary phase in the middle, and then some sort of decaying phase. And if I can divide this thing up and look at individual portions of the ground motion, I might be able to assume them stationary and estimate, say, power spectral densities. And I might be able to see how the power spectral densities changes from step 1 to 2 to 3 of the time series. But if we do it this way, we realize we're kind of giving ourselves a finite length signal of t, and as that t gets smaller, so we're trying to get more kind of time resolution in what's going on in the earthquake, right? We're going to have this trade-off that we're going to need a bigger bandwidth on the filter, so we're going to lose some frequency resolution to maintain kind of the same estimation uncertainty in the power spectral density. So this time-frequency trade-off has real implications for us in circumstances like this. Okay, so that's this frequency analyzer. I like this as kind of a viewpoint to get at this idea of the B and the T and the time and the frequency trade-offs for our power spectral density estimation. And you can see, again, we can use our tools from earlier in the class to get some understanding there. And hopefully that gives you a nice qualitative understanding, at least, of the impact of these finite length signals on our estimation. All right, then one last topic I wanted to flash real quickly here, just to give you kind of some high-level awareness, although we won't look at it in any level of detail. And I did mention a few slides ago about this issue of continuous versus discrete time. Most of the math we've been doing in this class is for continuous time. In reality, though, when we look at data, it's always going to be discretely sampled, and so that creates a couple issues for us. So One is that we have to do things like discrete Fourier transforms instead of continuous Fourier transforms, and we won't get into the details of that. But one thing I wanted to mention just in this domain of kind of the impact of real data on this estimation of these properties we've been studying in the class is about discretely sampled data also has some limitations in terms of high frequencies. And so let me try to spell that out a little bit. So let's say we've got kind of time and some observation, and because we're sampling discretely from, say, some sort of a measuring instrument, and it's either the ability of the instrument to sample quickly or our ability to store data or something like that, we're going to usually get, or we're going to always get, kind of discrete observations at points in time. And so while I usually draw lines for our kind of mathematical version of the calculations, our data is going to look something like this. And if we plot it continuously, and if these points are closely spaced, none of this really matters too much. But there is a higher, some issues with high frequencies relative to the sampling frequency that can be important. And what specifically happens is that I might be able to say with samples like this, maybe my continuous x of t that I would infer from this data is something like this light blue line. All right, so that would be a natural way to look at this. But there's also a possibility that the data from this is given by this red line. All right, so this red line is passing through all the data points. Try this again. Got that. So I'm still going to pass through these data points, but I've got a higher frequency oscillation going on to where I'm basically oscillating once every time between data points. And I wouldn't be able to tell the difference between the red signal and the blue signal given the sampling of those black points at that particular frequency. And so this higher frequency going on in the red signal isn't detectable. And so that basically the frequencies that are not resolvable from this discrete observation, they depend on the sampling rate and this calculation called the Nyquist frequency. And so I mentioned it here very briefly just to mention that if you're looking at kind of high frequency resolution from or kind of properties from some digital data, you may want to just double check that this Nyquist frequency isn't causing problems with your resolution. Okay, so that brings us to the end of this section. The goal here was really to think about estimating stochastic process descriptors, specifically that power spectral density for measured data, and think about some limitations. The primary limitation we were thinking about was when we have a signal of finite length, that we're going to get some estimation uncertainty in that power spectral density because of the finite number of data points we have to look at. And then we very briefly here at the end just looked at that Nyquist frequency issue of the high frequency resolution from digital signals. And I hope those are some useful context, again, to think about kind of broader ways in which the tools from this class can be used to understand these types of issues, and to think about, at least qualitatively, the practical implications for estimating these properties from real world data. Okay, so that concludes this section. Thank you.